Thank you. Yeah, don't try to pronounce my last name. It's even difficult if you're Swedish. Should have never changed. I work for a company in Boston called Shoebox. Not Shoebox, but Shoebox. And we do a lot of cool things that involve legal documents. And long story short, if you have a Delaware C corporation, which is basically what everybody has in the US, you need Shoebox. If you're going to do a startup, you definitely need us. You might not know it yet, but you do. The official blurb is the one down here. This apparently is designed to sound good to the type of people that starts companies. To me, it says nothing, because that's not me. So with legal documents, of course, with our system, you can sign them with a pen, print them out, sign them, scan them in, and upload them to the system. You can do that. But one of our benefits is that you don't have to do that. You can create the legal document in our system, sign everything electronically. People will get notified saying you have to look at this paper and read it and sign it, and it will get sent to the lawyer that then has to approve that everything is fine, and all this kind of stuff. Really long, big, complicated workflows for legal documents. And you can customize them, things like this. So we have loads of documents, and many of them are generated then through this system. And we have our own template language, unsurprisingly called Shoebox templates, or SBT, which is really Report Lab RML plus SOAP page templates, plus a little bit of extra magic and app-specific stuff. Both templates and documents can have revisions, and of course it would be nice to have a way of showing the differences, because there's loads of documents and there's loads of templates and there's several revisions of each template. So a text diff wouldn't do. We can't just run it through a text differ. A lawyer wouldn't understand anything of that. We need this kind of graphical diff with red and green texts. Should be easy to read and semantically meaningful, and that means that if you replace a word, it should show that in the diff that you have replaced the word. It should not show which characters that have changed in the word, because that is not readable. The first effort we made of making a diff of these templates, it worked, but it has less than optimal results. We often got things that was marked as being inserted or deleted when it shouldn't be. I'll show an example later. This was implemented by someone else than me, and I'm told that it took a month or so, so there's clearly faster programmers than me at work, because this work I did definitely not take just a month. Because diffing XML was trickier than we thought. So why not use somebody else's library? Well, there was one called XMLDiff, and it seemed to work, but it was unmaintained, which was the reason we didn't use it from the start. But since it was harder than we thought, we decided to take over the maintenance of XMLDiff. The last version was 0.6 at that time. It's not only library, it's also command line tool. So if you're on Linux and you have a command that's called XMLDiff, you install it, this is what you're going to get. You're going to get XMLDiff 0.6. So I was tasked with implementing document diffing based on this, and that was not difficult, but it also didn't give nice results. And here you have a good example. What you can see is that instead of inserting a new paragraph 3, which is what actually happens, because of the numbering, it will actually update the old paragraph 3. So it will delete almost all the text except an O and a the over there, and insert new text instead. And then it will insert paragraph 4 with the same text as what was there before. And it's actually worse than this, because then it deletes paragraph 5 and reinserts the old paragraph 4, new paragraph 5, it deletes it as number 4 and then it inserts it as 5. Only then it starts actually changing the number, showing the numbering difference for the rest of these sections. So the output was no good. But that wasn't the only problem. We also figured out that there was a memory leak in the C code because there were C optimizations to this. And I haven't done any major programming in C since the 90s. So it was not obvious to me where that memory leak was. The Python code also was very fond of two-letter variable names, like typical C, one or two-letter variable names, so it was hard to read. And the internal data structure was a hierarchical list of lists with the parent list contained as one element in the child list. So you had lists of infinite loops in hierarchies. So if you wanted to print out just one item, because the parent was part of that item and all the children, of course, was part of that item, you ended up printing out the whole structure anyway, which could be thousands and thousands of these lists of lists. And there was some infinite loop somewhere in there, maybe because of this data structure, we're not sure. Because once I figured out there was an infinite loop, where I had already decided to try something else, because it was also really hard to improve the matching and fix the problem we saw on the other page. So I ended up scratching all of XMLDiff and writing a new library, which we, after some discussion and deliberation, decided to call XMLDiff. So we have then released this as version 2. It's not like a separate package called XMLDiff 2. We quite brutally just deleted everything in the GitHub and stuck my stuff in there once it was reasonably finished. And we released that as version 2. Current version is 2.2 because obviously there was a lot of bugs and problems in the early versions. It's almost entirely incompatible. It's pure Python. We get better matchings. It's easier to use a library. And it supports formatters, which I will explain later what that is. So how do you actually diff anything? Before we talk XML, let's look at a simpler case, text files. And there's 3 stages to diffing. First is matching, finding bits that are the same. Then it's edit, making an edit script. I'll explain what that is. And then it's outputting this diff. So matching in text files, when you want to show a diff in a readable way, you typically do this line by line. So a diff in that case will simply split up the files, the 2 in files, into lines and look if they are the same or not. If they're not exactly the same, then they don't match. If they're exactly the same, they match. So it's very easy. But you can't just go line by line and compare. That's going to get complicated and it's going to get slow. Instead, you have this is a classic computing problem and it's well solved. It's called longest common subsequence. So you have an old list and you compare that with a new list and you get a longest common subsequence out. So that is basically the longest list you can find where all the items are in the same order in both of these lists. So for a text file, you'll run the longest common subsequence on the lines, or the LCS, as it's usually just called. And from this, we then get a list of lines that match. Then we edit. We make an edit script. And an edit script is a list of edit actions that will turn the old file into the new file. For a text file in this kind of system, in this way, when you have line by line, the edit actions are basically just delete lines or insert lines. You could also have move in theory, but discovering moves is not necessarily particularly easy. So often you just skip that. Depends also if you want to output it, because then if it's a move or if it's a delete and insert doesn't matter, because the output, if you have a visual output in a normal diff command, it's going to look the same if it's a move or if it's an insert and delete. if you want to store this in a compact format, if you want to actually store the differences, for example, in some sort of version control system, then you might want to implement the move. And then we use this edit script to make a nice looking output, like this. So that's not so hard, right? But if XML was this easy, I wouldn't have a talk. So let's talk about XML instead. First of all, let's talk about the matching. Here we don't match lines, we match nodes. The node matching is tricky for XML. Scientific papers on how to do hierarchical diffing, which of course is what you're doing when you do XML, generally view hierarchies as nodes that have a value and children and nothing else. That's all there is. So XMLDiff 0.6 did something very clever here. It converted the complex XML nodes into many simple nodes. For example, these two nodes here, a para node and a B node, gets converted into 6 simpler nodes, like this. You have a node with a para as a value, attribute node with section, value node with 3, which means that the section has the value 3, and another node with text, and then another text. So every node now only has a type, a value, and children, and comparison is now easy. But being clever is always dangerous in computing, because what happens then if we update the numbering? Well, these two nodes down here, they stop matching. And although these nodes have the same value, the children are completely different, so the similarity of these nodes get to be 0.5, which is right at the cutoff, so they get set to be not the same as well, these two. And that means we have this situation, because the top node has 3 children that are different. Two out of 3 children are different, so again that top node won't match, and the result is what we saw before. We get things like this. So you need to look at the node as a whole, not as independent pieces, to get good matching. I make a string out of these nodes, the attributes and the texts. So I just make a string like this, and then I use the standard libraries difflib to get the similarity ratio out of that, which actually uses the longest common subsequence method. If the node has children, I also take that into account in equal measure to the difflibs ratio. But if it doesn't have any children, I ignore that. And this works, but there's a lot of room for alternatives here. I, for example, tried to dealing with attributes separately from text, so you can have weighing. You can put in and say, oh no, text should be more important than attributes and children and things like this. But I did not significantly improve the matching. It matched as good or as bad as it did before. So I stayed for now with this. This may change in the future. I ended up here basically by trial and error. And then is again this overall matching procedure. We now know how to compare two nodes, if they are equal or not, but should we use longest common subsequence again to match the nodes? Well, you could do, you could flatten the whole tree into a list of nodes by traversing it, and then just use the longest common subsequence. But that will leave a lot of nodes unmatched that could be matched, so you can't just do that. It would get very bad. And the diffs would get very big, and we want them to be somewhat compact because they should be possible to store. Finding the best possible match over 2 big sets is usually called the stable marriage problem, and there's various algorithms for that basically compares every node with every node and tries to find the best possible matching over that. But doing that would have been crazy slow. So what I did is what I call single iteration best match. Maybe there's a good name for it, but that's what I call. I simply go through each node from one tree and find the best match for that node. And then I remove both nodes from possible matchings. So that means that the best match from the other node's point of view may be actually another matching. So we could still improve the matching here by using a stable marriage type matching. But this seems to be good enough. And it was also slow enough, so I stayed with that. Some documents could take 1.5 to 2 minutes, one of the biggest diffs and slowest diffs that we had. And we needed it to be seconds. So I didn't try the stable marriage versions. And then we have edit actions. With the linear file, we got just insert and delete, or maybe also move. But XML needs more. We need to be able to delete, insert, rename, and move nodes. But we also need to delete, insert, rename, and update attributes. We could theoretically move attributes as well, but then we have the same problem that it's not easy to find moves of attributes. And we need to update texts, both the texts inside the node and after the node. As we saw with this previous example, the text that are inside the paragraph is actually mostly hanging after the B node. And that means that that text ends up on the B node, not inside the paragraph. So that's two different actions. And we also need to insert comment as a separate action, because comments are just almost nodes. One problem I discovered when doing this is that with LXML, which we are using in the bottom here, you can't actually delete a top node comment. If you put a comment in your XML file before or after the root node, there's no way to delete that in LXML. Very funny little piece of information. Of course, we had that problem. Of course, we have top nodes in one version and not in another. Well, now we have a list of the node matchings, so we go over the tree again, node by node, and make this edit script. And if the node has a match, then we have to look at what the differences are between the new version and the old version of the node. Because it's not with text, it's exactly equal. This can be just a half match where some things have changed in the node. And then we have to then edit. We have to give out these edit actions for updating text or updating attributes or deleting attributes and things like this. If it does not have a match, we insert it, because we actually iterate over the new version here. That's the easiest. And lastly, all nodes from the old tree that doesn't have any match should be deleted. And that's how we then have an edit script. And from that we generate an output. And this is basically how the output looked from the old XML diff when you used it as a command line. It just prints out the edit actions. So there was several comments or edits, comments on or bug reports on XML diff here. They're saying we can't diff our files because it just never finishes. It just eats up all the memory, because they got into this infinite loop with the memory leak, which meant that XML diff would just slowly chew up all the memory and then crash. And then we figured out that they could actually diff it if we used the pure Python version, because there we didn't have memory leaks, and we could fix other stuff. And with my new version, we could also diff it and get the kind of output. And then people just go, well, I don't know what to do with this information, because this is the output they get. We don't want that, really. We want something like this, right? Where we have here now a span with a class that says delete to remove the 3, and insert the 4 with class insert. So then we can format this with CSS to get the right sort of colors and strikeouts. But XML doesn't really have any spans and things like this. So instead what we do is that we have a formatter. This is what we talked about, formatter. So one formatter just prints out the edit script as before. Another formatter will give XML output like this with special diff tags in a special diff namespace. That says what has happened. And here you go with that the attribute has been updated from 3 to now 4. And we have a diff delete tag and we have a diff insert tag. And then you have to format that to whatever output your XML should be with XSLT or something else. But XSLT would be the standard way of doing it. That can be complex if your format is complex. We, for example, had this fun little problem. We have XML that looks like this. This is basically sort of app-specific switch statement. So if the variable called expenses is set to bear own, then this should be shown. Otherwise, if it's reimbursed, then this should be shown. Things like this. And when we show the templates in a GUI mode, of course, both needs to be shown, and they need to be shown with this information plus some other information that I skipped now because this is simplified, otherwise it doesn't fit. And we have this as a part of an XSLT. It calls a function, and that function is a Python function. You can do that in LXML. You can stick in Python functions and pass that in and let the XSLT call it. And this function makes a title from the field, from this app term tag and the app option tag, and it creates a title from that. However, if app option is not a child of an app term, this function breaks. And that can happen after diffing. And how can it happen after diffing? It's a node mismatch again. In one version, a section of the document might be inside of this app term app option tags, and in a later version, it's not. It's inside something else, and this leads to mismatch because attributes of nodes and content is very similar. So we get a match. And the end result is XML that looks somewhat like this. This is pretty a lot of information here, but here we say that the app term has been renamed. So this section should just say section there. So this section tag used to be an app term, and one of the attributes have been deleted, and this whatever tag has been moved from inside the option to outside. And the option has been deleted, and this happens for the other option too. So we delete and insert here, that means move. And now the app option is not inside an app term, and that should say section here too. Sorry, I didn't see that before. This is the last things I changed this morning. So how to fix this? Well, we have to either fix the function to not break in this case, which is what we did, or you have to fix the XSLT to go, okay, here's an app option, but it has a delete tag, so ignore it, don't do anything. But most likely you don't do this kind of advanced stuff with XSLT and your XML. Most of you here is actually using XML in the specific implementation called HTML. You might have HTML documents that you want to diff, and you can do it with this. But then we come to the next problems, because we have formatted text inside of HTML and also inside of RML, which is what we're using. So if you add a little bit of formatting to some text, you get some very big effects. So here we just added a B tag here and an I tag over there. And this means that the old P had contained text that said this is formatted text. The new one has contained text this. So that's not going to match. These things are not going to match anymore. So what to do? Well, what we do is that we replace tags inside of formatted text with Unicode characters before the diffing. And this means that the nodes will now still match, because it's these Unicode characters, they weren't there in the old version, but this is still similar enough to match. And then after we've done the diffing, we'll unreplace this with the new tags and add the proper insert and delete attributes on those tags. And these characters are from the private user area in Unicode, so we're allowed to do it. It's not, won't end up by mistake being Chinese characters or Japanese characters. So yeah, this is how it then ends up afterwards, that we have a B and diff insert. Actually, if you set this up correctly, the formatting, it will say insert formatting, so that you specifically know that it's formatting, and then you can use another color for that, for example, or maybe a yellow background. So you don't have to show the deleted text with one formatting and the inserted with another. You just show the text and show that the formatting has changed. That's what we do. But as I mentioned before, it's very, very slow. The worst diff case we had took 1.5 minutes or more. So I went on trying to improve that. And one of the biggest speed ups I found was implementing a simple shortcut. If the match is 100% between two nodes, then stop looking for something that is better, because you're not going to find it. I also added a flag to choose between 3 different ways of calculating how different two nodes are. They're all a part of difflib. We now have accurate, which is the one I used in 2.0, that was very slow, which is using the LCS algorithm. And we have fast, which is a faster one that's good enough. And we have faster, which is not that great. It doesn't give very good matchings, but it's very fast. I also added a fast match option, which uses the longest common subsequence as a first step to find matches. So I still go through all the nodes that are unmatched, node by node, to find new matches and better matches for those. But the first thing I do is to flatten the trees to lists and use LCS on them to find a first set of matches and remove that. That won't give very nice matches always, because it won't look for the best match. It will just find a match that is in the right order. So if you move around nodes a lot, it's going to be terrible. But it speeds things up. So by the end, I had gotten down the time for a typical XML doc for maybe 20% of the time. Our worst case that we had took 8 seconds under XML Diff 0.6 with all its C optimization, and took 100 seconds under XML Diff 2. But I got that down to 5 seconds with default parameters. I think 20 something if you use the accurate matching. But 5 with the default one, which is good enough. With less accurate matching, you get down to 2 seconds. And if we also use this fast match LCS algorithm, we're down to 1.5 seconds. So it means we get better matching and faster diffing, even though we're pure Python compared to XML Diff 0.6. How do you then use it? You can, of course, use it from the command line. It has a help. You can look at it. But that's not so exciting. You want to use it from Python, right? And it has a simple API that's designed to be easy to use. So here is one example. You just do diff2 files. So you have a function here. And this function can either take file names or it can take open file objects. There's also a function to diff XML text, Unicode or binary text. And there's a function to diff LXML trees if you already have LXML trees. And the result you get in that case is an edit script by mode of Python objects. So you have different Python objects with the parameters that makes the edit script. But of course, you usually want this XML output. You want the formatter, and then you specify that. So you import the formatting, say XML formatter here, and here I've defined that the P tags, those have formatted text, and the formatting tags inside of that is I and B. Everything else that is not formatting tags will not get this format inserted, but just a normal insert, and will also be treated as one whole tag, including the contents of it will be treated as a tag and replaced. So if you change something there, it gets deleted and inserted because it's not formatting instead of just changed. And then you diff it and just pass in the formatter here, and then you get some XML out instead of this list. Well, we're using this, so we're not stopping. We're not going to let this be unmaintained. We're trying to fix bugs quickly if they show up. So far, we've succeeded. We have some requests for more options when matching, like being able to more accurately change if we should let the text be more important than the attributes and things like this. But we don't have much information to go on there, so we don't really have their use cases. So we would just be fumbling blindly if we implemented that. So we're waiting for more people to have more opinions. We like more flexibility when matching. It would be nice to have this stable marriage algorithm. I don't know how long it would take. Thanks to the other speedups I made, maybe it won't be that slow. That's all I have. Questions? We have a microphone for questions, so they can be recorded.
Does your algorithm also handle XML where the order of child nodes is not important and can change between versions of a document?
No, it doesn't. It will. If they change between documents, they will get moved. Yeah, but if they're the same, that's the only thing that will happen. They will just get moved. Thank you.